which goes to plus infinity, which goes to plus infinity. By the definition of our number, irrational number E, we have that the difference between 1 plus 1 over n to the power n minus e, the absolute value of, evidently, is less than epsilon for some n greater than capital N of epsilon, for any epsilon positive. It's the formula 4.24. I hope you know this. Yes? Only the definition of the value of the number e as a limit of a sequence. .24. Agree? Agree.
Yes,
Agree.
good.
Very good. So now we pass to the next slide. And if I take this sequence n sub k, which is also the sequence of natural numbers, then we have the same inequality, if I have n sub k, which is greater than capital N of epsilon. It's the formula 4.25. You see, in the previous slide, I have for any n, now I have maybe a special sequence, but also the sequence of natural numbers. So the same result holds true. And from this inequality 4.25, I have for this subsequence of natural numbers that the limit as nk goes to infinity, 1 plus 1 over nk to the power nk is also e. Agree?
Yes,
Yes.
Yeah.
Very good. Onya, clear?
clear.
C'est clair.
Oui, c'est clair.
Yeah. So you see, if I take an arbitrary sequence of real numbers, because in the formulation of our exercise or of our problem, we have p sub k with p sub k strictly greater than 1. And this sequence goes to plus infinity. Then for any sequence of p sub k, we can find a sequence n sub k of natural numbers such that p sub k is greater than or equals n sub k and less than n sub k plus 1. Evidently, in this case, n sub k goes to plus infinity. It is
Professor,
the, huh?
I have a question. Is only if it's 1, or for example, is 2 plus 1 over nk is the same.
Valentina, you can say that it will be p sub k less than nk plus 2. It is not important. Only some inequalities change only in the notation, but as for the idea, it will be the same thing. But you see, for example, Valentina, if you take a number between, for example, you take a number 78.5. It is greater than 78, a natural number, and 78.5 is less than 78 plus 1. Agree?
Yes, agree.
So your P sub k is between nk and nk plus 1, as usually. Okay?
Yeah.
Agree.
Okay.
You understand this inequality 4.27. Nice.
Yes.
So now if I have this inequality 4.27, then let us write two obvious inequalities. First of all, I take 1 plus 1 over pk to the power pk. Then you see, in this case, my denominator p sub k is less than 1, or is less than nk plus 1. So, first of all, it is clear that 1 plus 1 over pk is greater than 1 plus over nk plus 1. Clear?
Yes, it's clear.
From the other hand, you see the power pk is greater than or equals nk. So we have two numbers that are greater than 1, strictly greater than 1. So we have the first inequality. Agree?
Yes, agree.
Agree. Very good. So now I want to rewrite this inequality in the following way. You see, as a fraction, the numerator of this fraction is exactly the base. So 1 plus 1 over nk plus 1. But here, you see, I have not nk, but I take nk plus 1. So in order to keep the same thing on the left hand side, so I have to divide this value by 1 plus 1 over nk plus 1. Is it clear? We have the same thing, you see, Valentina, we have the same thing.
Yeah, it's clear for me.
Clear. Onya,
Yes, it's clear.
yeah. Eric, is it clear?
Yes, it's clear.
So it's you see why we have to do this passage, this rearrangement, because we know that the limit e is 1 plus 1 over n to the power n. So I want to have exactly the same expression, And if I divide this by 1 plus 1 over nk plus 1, the limit of the denominator will be 1. So nothing changes in the limit. Understand?
Yes,
I got it.
Yeah. Yes. So now,
perfect.
same thing as for the second inequality. I want to estimate my value. 1 plus 1 over p sub k to the power p sub k. So, first of all, you see, I make use of the fact that p sub k is greater than n sub k. So we take the denominator, the base, which is less than sub or p sub k. You see? So it will be evidently that the left-hand side will be less than the right-hand side. And moreover, I know that p sub k is less than n sub k plus 1. So I write the power n sub k plus 1. And then you see, I rewrite my value as a product. 1 plus 1 over n sub k to the power n sub k multiplied exactly by 1 plus 1 over n sub k. Clear?
Yeah, it's clear.
Clear. Now, you see, I do not write both inequalities. I hope you can do it yourself. So, but you see, I have that 1 plus 1 over p sub k to the power p sub k is from one hand is less than something in the inequality 4.29 and greater than something that the right hand on the right hand of the inequality 4.28. Then if I pass to the limit, as k or nk goes to plus infinity is the same thing, then by the theorem of two policemen or by squeeze theorem, we have that the limit of 1 plus 1 over p sub k to the power p sub k is e. So the equality, the formula 4.30. Clear? Agree?
Yes.
So no problems here. Very good. Now let's turn to the second limit in our exercise. So we consider an arbitrary sequence q sub n which goes to minus infinity. This means that minus q sub k is greater than 1 if we are dealing with the sequence which goes to minus infinity. Agree? If you have a confusion with n and k, it's the same thing.
Okay.
So let's set, we set q sub k is minus alpha sub k. N, in this case, if you want, n is 1, 2, 3, 4, 5, so on, k, k plus 1, and so on. Same thing. So if I take next line, if I take 1 plus 1 over q sub k, where q is negative, to the power q sub k, then I replace my q sub k by alpha sub k. So it will be 1 minus 1 over alpha sub k to the power minus alpha sub k. This is only by the definition of my quantity q sub k. Agree?
Yes, agree.
Agree. So now we go to the common denominator, then we'll have a fraction alpha k minus 1 over alpha k to the power minus alpha k. Same thing as in the previous step of our rearrangement. Agree? Nothing special.
Yes, agree.
Valentina, agree. Thank
Yeah.
you. So now you see the power of our base alpha k minus 1 over alpha k is negative. Then we pass to another step. We write that it will be alpha sub k over alpha sub k minus 1, but to the positive power alpha k. Agree? Valentina,
Yeah, agree.
agree. Onya, agree?
Yes, agree. C'est clair.
Eric, est-ce que c'est, is it clear? Is it clear? Eric, Hussein, is it clear?
Yes, it's clear, sir.
Good, thank you. So now, we have to rewrite our fraction alpha k over alpha k minus 1 in the following way. So I write that it will be 1 plus 1 over alpha k minus 1 to the power, you see, to the power, first of all, to the power alpha k. But I want to have as a power exactly what we have in the denominator of the second term of our base. You see? So I write the power as alpha k minus 1, but multiplied by 1 plus 1 over alpha k minus 1. And attention, please, alpha k is greater than 1. So we have as in the base, the sum of two positive numbers, and it is multiplied by 1 plus 1 over alpha k minus 1, so it is also It is also the sum of two positive numbers. Then, if you want, we can apply the first limit. So, in some way, if you denote alpha k minus 1 as p sub k, then for the first term, we have that this term goes to e as k goes to infinity, and the second term, the limit is 1. So our limit theorem gives us that this limit is e as k goes to infinity. That is the second limit in 4.24 is also proved. Agree?
Totally.
Yes.
Yeah, I agree.
Thank you. So now, especially for Valentina, we will consider some examples with the number e. The first example is the following. So I want to calculate the limit. It's a very simple example, so you can see that I want to calculate the limit of 1 plus 1 over n to the power n plus 5. Here, you see, in fact, I do not write this. I hope you know this already. So we will make use of the limit theorem. How to use this theorem? So I have the limit of something to the power n plus 5. Yes. So it will be the limit as n goes to infinity of 1 plus 1 over n to the power n multiplied by 1 plus 1 over n to the power 5. Agree? No problem. Hussein, clear?
Yes, sir. It's so clear.
It is clear. Then we say in the framework of our limit theorem, we say if two limits exist, then the limit of the initial sequence will be the product of the limits. So in this case, it is very easy because we know that the limit of 1 plus 1 to the power n exists. It will be e by the definition of this number e. And then you have also the limit as n goes to infinity of 1 plus 1 over n to the power 5. So the second limit is 1. Why? If you have this question, I can explain you that in fact you have the product of 5 limits like 1 plus 1 over n. Each limit is 1, so the product is 1, and then the initial limit will be e multiplied by 1, that is e. Agree?
Yes, I agree.
Very good. So the second exercise, it is rather the same thing. You see, in this case, you have a very simple situation. We do not need to use our previous exercise about P sub n, for example. But in this case, we can deal only with some known results. In this case, you see, I know by my limit theorem that the limit of the sequence 1 plus 1 over n to the power 3n will be the product of the limits 1 plus 1 over n to the power n, same limit, so 3 times. Each limit is e. Then the limit of my sequence 1 plus 1 over n to the power 3n is e cubed. Okay?
Yes. Yes, Professor.
No problem, I think. I hope. So now we have another exercise, exercise number 42. Here I want to find the limit as n goes to infinity of 1 plus 6 over n to the power n. You see, in fact, here we have a rather simple limit, and in fact, we can use also the limit theorem, but I propose you some other point of view to this exercise. So if I write that 1 plus 6 over n to the power n will be, if I introduce the notation as an exercise number 40, p sub n will be n sub x. It's the notation. In this case, I will have that I have to find the limit 1 plus 1 over p sub n to the power 6 p sub n. Because if n, or if p sub n is n over 6, then 6p sub n will be exactly n. Agree?
Yes.
Понятно. Est clair?
Oui, c'est clair.
Merci. So I rewrite this limit in the following way, like 1 plus 1 over pn to the power pn, and all this to the power 6. To the power 6. However, you see, for the moment, it is a tricky way to find a limit, because you do not know the properties of the so-called continuous functions. You see, first of all, I write that the limit as n goes to infinity, then the square bracket, and the power 6, you see? And then I write that the limit of something that is 1 plus 1 over pn to the power pn, and all this to the power 6. You see, it's the property, in fact, it is the property of the continuous functions. We will see this if, in fact, it is roughly speaking, blah, 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 if you want, that I can put my limit in the bracket. It's for you, but you see, in fact, we have something in brackets to the power 6. So we can take a product 6 times of the same limit, and we will obtain the same result, e to the power 6. What do you think about? Questions? Onya, c'est clair.
Oui, c'est clair.
So I explain once more. You see, in fact, we have in the square bracket, we have a continuous function. I can write it like x to the power 6. It is a continuous function. So I can put my limit into the square bracket. But in this case, we have 6, a natural number. So in this case, we can take a product of 6 terms like limit 1 plus 1 over Pn to the power Pn, and we will obtain exactly e to the power 6. Agree? Eric, agree?
Yes.
Yeah.
Valentina, agree? Hussein,
Yes, I
agree?
Yes, I agree.
Thank you. So now we pass to another example, which leads also to the number e. So we want to find the limit as n goes to infinity of n over n plus 1 to the power n. So first of all, we transform our base. So we write that it will be the limit in the numerator. N can be represented as n plus 1 minus n plus 1 minus 1. Then it is easy to see that we have the base 1 minus 1 over n plus 1. Same thing. Then my idea here is to use our exercise number 40, but the second limit. So I write that my sequence q sub n will be minus n plus 1. Then only the notation in this case. Then as the base, what do we have as the base? We have 1 plus 1 over q sub n. But the power, you see, our power is n. So if I write that, if I want to have q sub n as the power here, so I have to multiply my q sub n by n over q sub n. In this case, the power will be exactly n. Agree?
Yes.
Yes, I agree.
Agree.
Yeah.
So now, you see a very complicated formula. So something in the square brackets, what do we want? We want to use the limit as q sub n goes to minus infinity. So the second limit in our exercise number 4. And I rewrite something in the square brackets to the power n over q sub n. Here, I know, I hope you know also that a sum a to the power x is the exponential function of x log a. Agree? You know this formula. Valentina, you know this.
I don't remember very well, but I am searching.
So you have to believe. You have to believe me. So then you can check on the web. Okay? So now, what do we have? I want to rewrite my limit as the limit of an exponential function using this formula. You see, in this case, a is 1 plus 1 over q sub n to the power q sub n, and x is n over q sub n. So I use this formula in order to have that our limit is the limit of the exponential function of n over q sub n multiplied by log of 1 plus 1 over q sub n to the power q sub n. So I rewrite my limit using this formula for a to the power x. Agree?
Yes, sir.
Nothing special. Only Hussein. Agree?
Yes, Professor, I agree.
Thank you.
No.
So now, here we have the same trick as in the previous example. So we make use of the fact that our exponential function is a continuous function. So the limit of x of the exponential function of something will be exponential function of the limit. We will see this fact in the second part of our seminar. Now, please believe me, if it is possible. So we have that our limit is the exponential function of the limit of the product n over q sub n and log of the square bracket. You see this on the slide. Agree?
Yes, I agree.
Yes, I agree.
Yeah, I
So
agree.
the only one thing you have to believe me that as for the continuous functions, you can change, I say, the function and the limit. If you have the limit when n goes to infinity of f of x sub n, and the function is continuous, then you can write that it will be f of the limit of x sub n. So it is exactly the same situation in this case, and we write it like this. Okay? So now, due to our limit theorem, we know that if two limits exist, then the limit of the product will be the product of the limits. As for the first sequence, n over q sub n, then this limit you see in the square brackets. I have denoted this, and this limit will be -1. As for the second limit, we know that, first of all, you see, in this case, we have to put the limit as n goes to infinity in the logarithm, because this logarithmic function is also continuous for rather large x or rather large n in this case. So the log of e is 1, and finally we have our final limit, the limit of our sequence n over n plus 1 to the power n, and this limit is e to the power -1. Do you have some questions? In this case, maybe, but the only thing you have to believe me that working with the continuous function and the limits, you have to do this. You will do this maybe in 1 or 2 seminars without problems, but now you have to believe me. Question? Valentina, is it clear?
Yeah, it's clear.
Yeah, it's clear. But really clear. You see, the only thing here in this exercise is to change the name of the function and the limit.
Okay.
The name of the function, for example, the exponential function, the logarithmic function, and then all the things are very, very clear. Are you agree?
Yes, I agree.
Yes, it's a
Thanks.
Yes, Professor, I agree. It's clear.
Thanks. So we will see this. Don't forget about these exercises, but in fact, you will see that you will work really mainly with the limits of function and not with the limits of sequences, mainly with this. So once we have some special definitions for the continuous function, for the limit of a function, and so on and so on, you will remember these examples and you will see that it is true. Agree? If not, we can return to these exercises. But now I think it is necessary to believe. Okay?
Okay. Okay.
Okay. Now we have the last slide, the last slide of our topic, the limit of a sequence. We have to know something about so-called recursive sequences. So the first example, you can see it. We want to study the limiting behavior of a sequence U sub n, which is given by, in red, U0 is A, some real number, and then for any n natural n, we have that U sub n plus 1 is un squared. So you see the recursive sequence we define as a relation between the next term, so u sub n plus 1, and the previous one, the term u sub n. In this case, we have a very simple relation. So I hope that the idea will be rather clear. Then, first of all, let's calculate. You see, why I want to calculate the first terms of my sequence u sub n? Because in this case, in this simple case, it is possible to give the formula, the general formula, for the nth term of my sequence. It is a recursive sequence, but for some recursive sequences, we can find the nth term of our sequence. In this case, you see, I calculate u0 is a, u sub 1 is a squared, u sub 2 is a to the power 4, u sub 3 is a to the power 8. Agree?
Yes.
Yes.
Agree.
Nothing special, nothing special. So my hypothesis is that the general term of my recursive sequence u sub n is a to the power 2 to the power n. It's the formula 4.31. But it is, for the moment, it is only my idea, you see. So I have to prove this, and in order to prove this hypothesis, I use the method of mathematical induction. So for n equals 1, we have u sub 1 a squared, so it's good. Then if I suppose that for n equals k, my formula 4.31 is true, then I set that u sub k is a to the power 2 to the power k. Now I have to prove this formula. I have to check my formula for the case n k plus 1. So by 4.3 or 4.31, I have that uk plus 1 is uk squared. uk, we know by our hypothesis that u sub k is a to the power 2 to the power k square, then the easy calculation gives us that it will be a to the power 2 to the power k plus 1. So our hypothesis 4.31 is proved. Agree?
Yes.
No problem.
Yes.
So the first here it is a simple situation. So we have a very simple result now because now we know the nth term of our sequence. So we pass to the second slide and we can have the following limit result. So if the absolute value of a is strictly less than 1, then u sub n goes to 0 as n goes to infinity. Why? Because we have considered an example, limit of q sub or q to the power n when the absolute value of q is less than 1 and the limit was 0. Do you remember this?
Yes.
Yes. So as for the first statement, there is no problem. Then if I take that the absolute value of my a is 1, then u sub n goes to 1 as n goes to infinity. Here, the question, is it clear or not?
Yeah, it's
Yes,
clear.
clear.
You see, I have a question to you. You see, for example, if I have a minus 1, is it really the limit of my sequence? Is it really 1 the limit of my sequence? And why? Maybe there is no limit in this case. What do you think about?
Is what? What is the sequence?
You see, Valentina, you have this sequence a to the power 4.31. Okay,
Yeah.
then I take a equals minus 1. So the absolute value of a is 1. No problem. Okay.
Yeah, so it's supposed like
So
this
why
tends to
the question, Valentina? The question is why the limit of this sequence is 1. Maybe the limit does not exist.
mm,
What do you think about?
I
Attention.
think
The
is
power, Valentina,
I think
is the power of a is the multiples of 2. So it will be always 1,
yeah,
even if a is minus 1.
yeah. If it's minus 1, this absolute value is also 1. So
Yes.
tends to 0. The limit tends to 0.
No,
Tends to
no,
1.
no,
Tends
to
to 1.
1. Agree, Valentina?
Yeah.
Onya, is it clear?
Yes. Yes. It's
Hussein, clear?
Yes, Professor, it's very clear now.
Eric, you see, it is a special situation. If we have, it is, I don't know the formulation of the problem to this case, but if we have a to the power 3 to the power n, it will be another thing. Attention, okay?
Okay, Professor, yes.
So the last case, if the absolute value of a is greater than 1, evidently this sequence u sub n goes to plus infinity. I hope you agree.
Yes, I agree.
yes.
Yes? Very good. So the next and the last exercise in this topic, we are going to study maybe a more difficult situation. So we consider the recursive sequence given by u sub 0 is 1 and u sub n plus 1 is the square root of 1 plus u sub n. You see, here we have, as it is stated in the formulation, we want to study the limit in behavior, that is to find the limit if this limit exists. So as for the moment, we cannot propose, I cannot propose any idea about the nth term of our sequence. So the only thing which we have is this formula, is this relation between the n plus 1 term and nth term. So usually, in this case, people use the monotone convergence theorem. So we will apply this theorem and we will done, okay, the proof or the analysis, what you want, in 3 main steps. The first step, you see, due to this monotone convergence theorem, what do we want? If our sequence is increasing and bounded above, then the sequence has a limit. If our sequence is decreasing and bounded below, this sequence has a limit. So the first step is to find the monotonicity of our sequence. So in order to have some information about the monotonicity, we will consider the formula 4.32. So in fact, you can read this, that step 1, we want to show that our sequence u sub n is monotonically increasing. So to this end, I consider the difference u sub n plus 1 minus u sub n. Using the formula for my sequence, I write that u sub n plus 1 is this 1 plus u sub n, and as for u sub n, it will be the square root of 1 plus u sub n minus 1. Clear?
Yeah, it's clear.
Yeah, it's
Absolutely clear. Then, as usually, I say maybe it is not very good, but I say that I multiply the numerator and the denominator by the conjugate. So I multiply my difference by the quantity square root of 1 plus u sub n plus square root of 1 plus u sub n minus 1. And I divide also by the same quantity. Then in the numerator of my fraction, the right hand side of the formula 4.32, I have u sub n minus u sub n minus 1. Agree? And divided by the square root of 1 plus u sub n plus square root of 1 plus u sub n minus 1. I agree. Agree?
yes,
Valentino?
yes, I agree.
Yes, Professor, I agree.
Good. As usually, if we are dealing with such kind of sequences, in order to prove that the fact that our sequence is monotonically increasing, we make use of the mathematical induction method. So S4, you see, if I take n equals 0, the first step, as we say usually, the base of induction, u sub 1 minus u sub 0 is positive, and u sub 1 is greater than u sub 0. So as for the base of induction, it's good. Now, I will suppose that u sub k minus u sub k minus 1 is positive. Then, you see, if I suppose this, then from my formula 4.32, I will have that the numerator of the fraction on the right-hand side will be positive due to my assumption, due to my hypothesis. Then the left-hand side will be also positive. Then I can say that u sub k plus 1 minus u sub k is positive. And our method proves that our sequence is monotonically increasing. I agree.
Yeah.
Onya, c'est clair.
Oui, c'est clair.
C'est clair. Merci. So the second step, if you want, we have to prove that our sequence is bounded above. You see, here I take a constant 2, but in the same way, you can take 3 or something, 4, 5, and so on. Some fixed real number. But 2, in this case, it's enough. For example, the base of induction, because we make use in this proof the mathematical induction method. As for n1 and 2, we see that u sub 1 is square root of 2, so less than 2, and u sub 2 is also less than 2. So the base of induction is good. So if I suppose for n equals k that u sub k is less than 2, then from the evident inequality, in the case n equals k plus 1, we have that u sub k plus 1, which is by the definition of our sequence is the square root of 1 plus u sub k is less than square root of 1 plus 2, that is square root of 3, it is less than 2. Then by this method of mathematical induction, we have exactly that the hypothesis 4.33 is fulfilled. So it's good. Then what do we have? By step number 1, we have that our sequence is monotonically increasing. From step number 2, we have that our sequence is bounded above. Then the monotone sequence theorem implies that our sequence u sub n has a limit. Agree? It is not very fast.
Agree.
Agree. Good. So now the last step, a very interesting step, because our question is to find the limit of our sequence. We have proved that the limit exists, but how to find the limit? So the step number 3, I say that the limit of my sequence is A. I denote the limit of my sequence by A. Then you see we have the relation between the n plus 1 term and nth term. Then let's pass to the limit in this equality, in this relation. On the left-hand side, as n goes to infinity, I have A, and on the right-hand side, I have square root of 1 plus A. Here, you see, as in the previous exercise, square root of x is a continuous function, so we can change the function and the limit. So we pass to the limit under the square root of something, and we have 1 plus A. Is it clear? Because it is important here.
Yes, it is clear.
Clear? Hussein, is it clear?
Yes, Professor, I agree.
Eric,
Yes, it's clear too for me.
Valentina,
Yeah, it's
Onya,
clear.
and the others, Okay, so you see, in fact, we obtain a simple equation which enables to find the limit A. So here we have the equality between two positive values, then squaring this equation, we find the formula. We can find two roots of two solutions to this equation, which are given by the formula 4.34. Then you see, we know that A is non-negative. Then in this case, we can take only one value of the limit, which is 1 plus square root of 5 over 2. And this is the end of this exercise. The question, is it clear or not?
Yes, it's pretty understandable.
Hussein,
Yes, yes, I agree.
Onya,
Yes. It's
Valentina, other people,
Yeah, it's clear.
Yes, it's
Clear.
clear.
very good. So now we have a break. Michael, very good. So we have a break and then we pass to the limit of a function. Okay?
okay.
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 See you.
Okay.
See you.
See you.